asynchronous programming. If you've written code to access files, to access websites, to perform long-running computations, there's two kind of ways in which you can do it. You can do it synchronously, which means that it runs in line with all your other code. So your code gets to the download or the file open, whatever. It waits. That operation happens in time with the rest of the code, and then the rest of the code keeps going. The asynchronous way is to kick off a background operation that runs at some time in the future, and when that finishes, it will rendezvous with your code. So your code keeps going while this other stuff is happening. And why do we care about this now? Well, like I say, the cloud is definitely one of the factors in there. Data is getting larger and it's getting further away. So we're dealing with stuff that is up on the web, we're dealing with files that are on servers on the other side of the world, and we're dealing with, say, large video or audio files rather than maybe text or Word documents. So that means we've got greater latency. It takes a long time to open a file on the other side of the world. It takes a long time to download a file from the web. And at the same time, with the move towards natural user interfaces, users' expectations of the responsiveness of the UI are getting higher. So in the good old days of batch processing, the user could submit a job, you could churn on it for days and they wouldn't complain at all. Now you freeze up for 5 seconds and you get all sorts of people go, oh man, the application's frozen, oh it's dead, oh this application stops all the time. That's with the keyboard and mouse in the way. We're moving towards things like touch input with tablets. There's the things like the Kinect, which are gesture driven. So that intermediate layer of technology is kind of getting out of the way, and that means your UIs need to be that much more responsive. Any judder, any jitter is going to be much more obvious when there's no mouse or keyboard in the way. And in fact, in Windows 8, we're seeing this becoming enforced at the platform level. So the people who built the Windows runtime decided that responsiveness was so important that any operation that could possibly take more than 50 seconds was not going to have a synchronous version. So if you look for say the file.open method in the Windows runtime, it's not there because the Windows runtime guys were afraid that you would open a file on the other side of the world and drag the interface to a halt. They've only given you asynchronous methods, begin open file async, that kind of thing. The other reason that this stuff is becoming important, you may be saying, well, okay, data is bigger, it's further away, but we've got fast networks now. But, well, we don't, because of this. Now, okay, we have data plans on this, but your phones, your tablets, as more people are using phones and tablets, we're coming back to kind of dial-up speeds. Maybe a little bit better than that, but still high latency, slow access. Now, this requirement for asynchrony is nothing new, and in fact it's been supported in the .NET platform since version 1. We've always had, for example, the begin and end pattern, where you've got, for example, in the web request, you've got the GetResponse stream, the GetResponse API, but alongside that you've got begin GetResponse and end GetResponse, which can kick off an operation in the background and then rendezvous later on to pick up the results. In .NET 2.0, there was also an event-oriented approach introduced, the background worker component, which was designed to work with Windows Forms or with other user interfaces, where it would run some long-running activity in the background and then raise an event. You could subscribe to that event and get the result. And in .NET 4, there's also a version for .NET 3.5, but it was folded in .NET 4. We have the task parallel library, which wraps up asynchronous activities, asynchronous computations into objects called tasks, which you can then pass around. They've got APIs of their own, like continue with, and you can process them. You can manipulate them as objects. But all of these bring with them some big challenges for the coder. And the really big one is just readability and writability. Asynchronous code has traditionally been much harder to read and to write and to reason about than synchronous code. In synchronous code, you've got a kind of top to bottom flow. You think of the flow of actions that you want. I want to download a file, I want to read the contents of that file, I want to parse out certain information from that file, and I want to go and download the other things that are mentioned in that file. And that's a pretty simple, conceptually that's a pretty simple flow. The problem with async code is that it tends to break up that flow. So because things are handled on callbacks or events or task APIs or whatever, you don't get that simple explanation. The code does not describe the logical flow. It describes some low-level stuff about how the asynchrony is managed, which really clutters things up. There are also complications around exception handling and resource management. So if you're using something like a callback or event model, then your exceptions are going to be happening in several different places, inside your callbacks, inside callbacks from those callbacks, goodness knows where. If you've got, say, a using statement to dispose a resource, then you need to make sure that somehow that resource survives from the initiation of the async operation to the completion of the async operation and gets disposed correctly even if the async operation fails. And this isn't rocket science by any means. It's certainly doable, but it's also very easy to do wrong. It's very hard to read the code that results from it. It's very hard to understand and prove that code is correct. So let's take a look at the problem as it stands. So I've got a simple application that does pretty much what I told you. It's going to go out to a web location. It's going to get the contents of that. In this case, it's an Atom feed. It's going to parse out the image references from that Atom feed, and then for each image URL, it's going to do kind of the same thing again and load the contents of the image into a bitmap and display that in a WPF application. This is where I take my life in my hands because I'm not convinced that this website is going to be up all the time. Let's see how it goes. And I've lost my mouse. There we go. So if we do go. Well, that wasn't a very good demo because, of course, unfortunately, Microsoft had provided me with a good network, which is exactly what I don't need for this. So everything downloaded so quickly that it actually looked like it was being pretty responsive. So let's try a different scenario. So this is where I really do take my life in my hands. I unplug my network cable. I hope my phone is going to do its Wi-Fi sharing. If not, this could be a really short talk, so wish me luck. And let's bring that up again. So you can see at the moment that's responsive. When I click the go button, it's going to start that download. Now it's gone dead. I can't even move that window. And obviously in this case it's a slightly artificial scenario because I do have a fast network lying around, but like I said, a lot of people using applications nowadays are doing so. Yeah, there we go. Right, this is going to go well. The Wi-Fi sharing on this has not been 100% helpful so far. As you can see, when things are running slow, when the synchronous operation is taking a while to complete, the application goes completely unresponsive. It is completely dead to the user, and that is an unacceptable experience for them. Fortunately, as I say, we can get around that by using the begin and end APIs. So here I've got something similar, except that I'm using web request, but I'm using this begin get response. And in order to have something happen with the result of that web request, I'm passing it a callback, and inside my callback, I'm doing all of the work. And this actually works pretty well. Admittedly, I'm not having to handle any disposable resources. I'm not worrying about exceptions. I guess from the last demo, maybe I should be. But you can see the complexity of the code is considerably greater. It's a lot harder to reason about. It's a lot harder to see that this code is correct because it keeps going forwards and backwards and sideways and up and down. On the positive side, you can see that, okay, you're going to be like that. I'm going to plug my network cable back in. On the positive side, you can at least see that it's responsive. I hope you could see that it was being responsive even while the images were downloading, but the code is really hard to read. So, in C#5 and Visual Basic 11, the language teams at Microsoft have introduced some new syntax to make it a lot easier to write asynchronous code. The syntax is going to be the same. I'm going to show you C#. The VB11 keywords are exactly the same, apart from the all-important difference that they use a capital A instead of a small a, so do bear that in mind. These keywords depend on stuff that is in the 4.5 version of the framework. They'll work on both the desktop and the Windows Store, Windows 8 profiles. They work on the desktop or the Metro profiles. There is an open source project called Async Bridge, which ports some of those requirements back to .NET 4.0 so that you can use the C#5 compiler and the async features on .NET 4.0. I believe Microsoft also have what they call the async targeting pack in the works, which will be an official component. So, what are these new features? Well, it's just two small keywords, and I say the same in C# and Visual Basic. There's async as a method modifier and await as a new keyword. The await keyword is only a keyword, by the way, inside async methods. So if you've already got, if you're already using await as a variable name, it will not clash. The C# compiler is pretty smart about this stuff. When you apply async to a method, what you're telling the caller is, this method may return before it's finished. And that may seem a kind of odd thing to say, because we're kind of used in C# and Visual Basic, we're kind of used to returning being the end of the method. But that's no longer the case with async. What this is saying is that if you call an async method, then it can yield control back to the caller, and the caller can carry on doing its next steps, even though the async method has not finished all the work it needs to do. So for example, it may mean that the async method has kicked off its download, but it hasn't yet completed the download. It's a little bit similar to iterators. So if you're writing an iterator, you use yield return, which means that the thing that's consuming your IEnumerable gets to run the next bit of its loop or whatever. It gets to take control again. But your method remains kind of suspended. It remains hanging around with more work to do after the yield return happens. And async methods are like that. Inside an async method, you can have an await. And await says, take this asynchronous operation and do not proceed with this method until that asynchronous operation is completed. So in this case, for example, we're kicking off a download string async, and what await is saying is don't proceed to the next line until that asynchronous download has completed. But it's also saying don't block, which means it's got to yield control somewhere else, back to its caller, back to the WPF message loop, or whatever. So it's kind of, again, like yield return. It's returned from this method for now, but the method may be resumed, hopefully will be resumed, later on when the operation that we're awaiting on has completed. So let's take a look at how that actually appears in practice. So here's that same code, that same asynchronous download using the new keywords. And I'll just bring up the synchronous version side by side so that you can compare them. So there's the async method, and you can see it's doing that same create a web request, but now it's calling getResponseAsync rather than getResponse. So that's kicking off that download in the background. Now usually we'd need to pass something like a callback to that, but instead of doing that, we're using this await keyword. If I look at getResponseAsync, you can see that getResponseAsync returns a task of web response. That's a computation in progress that will eventually result in a web response object. But what response gets turned into is just a web response. So it's like the await is kind of stripping off the taskiness by not resuming until the result is actually available. Similarly, when I get to here, I'm going to do a read to end async rather than the blocking read to end. And again, this is a task of string, but the result is going to be a string because it's going to strip off the taskiness, it's going to strip off the asynchrony without blocking the calling thread. So if we run that up and set that going, you can see I'm going to try my phone again.
Why not put a sleep in the
I'm sorry?
Why not just put a thread sleep?
I can put a thread sleep in the method. The reason I want to show this is because I want the asynchrony to actually have the delay has to happen inside the getResponseAsync. If I show you, if I put a thread.sleep in here, this method in my code is running on the UI thread. So I put a thread.sleep in there, I'll block the UI thread. I need the delay to happen inside the getting of the web data, which is happening in the background. Does that make sense? If only it were that easy, eh? So you can see that UI is remaining responsive even as it goes out to the website. And with a bit of luck, we will actually get some, no, still no luck, not a happy phone. All right. But I hope, despite the fact that that it comes up so quickly that you can't distinguish it from the actual synchronous behavior, I hope you are persuaded that UI is remaining. Next time I ask for a slow network. I hope you are persuaded that the UI was remaining responsive while that quick get was going on. And indeed you saw when I had it hooked up to the phone, although it did eventually die rather than downloading cats, you could see that I was able to press buttons, I was able to move the windows around, all of that sort of stuff. The UI remained completely live and responsive, even while a disaster was happening in the background. It was not being blocked. And yet when I look at that code, it's got that same top to bottom, easy to follow feel that our original synchronous code has, except it's responsive. When you start getting into more complicated scenarios, this stuff actually gets even more useful. So, as you've seen, I've not been handling exceptions. Did you guess? And if you think about how you'd handle exceptions in the begin-end scenario, again, that would be quite a lot of noise, it'd be quite a lot of mess, it'd be quite hard to follow where all the various different exception handlers were. Whereas in the synchronous version, you would just put something like a try at the beginning, a catch block at the end of the method, and again, your logic would be very clear. These are the errors that I'm going to handle, and this is how I'm going to handle them. No matter where they occur in the method, it's all handled in this one catch block, or one set of catch blocks, as opposed to having separate catch blocks for all the various callbacks. So, how does async help us with that? Well, here's the async version handling exceptions. So I've got a try catch around my entire method body. And so no matter whether that happens in the synchronous bit, in the immediate bit, or whether it happens in one of these awaits, or after one of these awaits, or in this thing that I'm calling to download an individual image, no matter where that happens, it's going to get caught in that. So you can see I've centralized my exception handling, and it's as clear as in the sync method. So hopefully my exceptions will work for me this time. And with a bit of luck, we should be seeing some complaints in here. There we go. So because I didn't plug my network cable back in, I've got a bad HTTP request, and I've not had to worry about putting a separate exception handler around my my end get or whatever in the old school API. I'm just able to express my exception logic at the method level, at the block level, without worrying about the details of the asynchrony that's going on in the background. One thing that's important to understand about this is that async and await do not give you any new ways to create asynchrony. They, for example, if you declare a method as async, that doesn't mean it's going to run on a background thread or anything like that. All it means is it can take advantage of the syntax for handling asynchrony in a friendlier way. An example of this is, for example, if you want to support cancellation or timeouts, then async and await are not going to offer you anything new. You need to be calling an API that supports cancellation or timeouts. So let's take a look at that, for example. So here I'm going to make my download cancelable, and as you can see, all I'm doing there is passing through a cancellation token, and that's why I've had to switch over to this HTTP client API. You saw I was using web request earlier because I wanted to show you the begin-end pattern. HTTP client is an async only thing, it supports cancellation. It's got a bunch of really nice helper methods on it, and it's kind of a really convenient way for working with HTTP in an asynchronous way. Now that we've got this await keyword, it's actually just as easy to use as the classic web request, if not easier, because you've got these handy helpers like reader string async. So notice here that await is not doing anything about cancellation at all. It's just passing I'm just passing that token through explicitly. But the exception handling does support me here, because if you do cancel an asynchronous operation, or if you cancel this particular asynchronous operation, it will raise this operation cancelled exception. And now I can handle that in a very natural way. So I can keep my download off. I can see that I'm still responsive. And if I get bored, I can cancel it, and should have probably put a breakpoint in there. And sorry, I should have tried to get a few of the cats downloading and cancelled it halfway through, but as you can see, they tend to be coming all or nothing at the moment. All right, so before we go on to that, actually, I want to show you a couple more things. Let's just... Sometimes you're actually going to want to do stuff with the results of an asynchronous operation. So if we're downloading files, for example, if we're downloading files asynchronously, the user may not know how many files to expect. The user may not know whether we finish on. It's the curse of the ever-expanding list box of is it done yet? Is it done yet? Is it done yet? Well, no, it might be just one more coming along. So sometimes it's really useful to be able to represent the progress, or at least the completion of an async activity. But all of the async methods that we've seen so far have given us, they've been basically fire and forget. So we've kicked them off, but we've not had any way of getting of knowing when they're completed, or if they're completed, or anything like that. They've gone off on their own and done their thing. The async keyword supports returning tasks, and it does so in a very easy and convenient way that may look a little bit odd at first but soon becomes very natural. So here's a version of the download images function that is basically the same as our original async function, except that it returns a task. And this may look a little bit odd because if you look at the body of that method, there is no return statement in there. We can actually see this even more clearly with the single download. So if we compare that to the single download here, you can see there's pretty much an exact line for line match between the version that returns void, the fire and forget version, and the version that returns a task. But once again, there's no return here. All we have to do to return a task from an async method is change the signature, just put task instead of void. There are a couple of little subtleties that you need to watch out for though. So for example, in my original download multiple images async, I was doing a fire and forget to download each individual image. Now, if I did that in the task version, then the method would get down to here. It would then fire and forget all of those things. It would then fall out the bottom, and the task would appear complete because the async method had now finished, but the fire and forget downloads would still be happening in the background. So what can I do about that? Well, the first thing I need to do is have some way of monitoring the progress of each of the individual downloads. So that's why I modified that to return a task. And now I can actually look after those tasks and use those to figure out when the main overall multiple download is allowed to complete, is allowed to finish. The simplest modification would of course be to just do in my for each, I would add an await, but that's not going to work, or if it's going to work really badly, because that would kick off the first download of an individual image, it would wait for the results of that, then it would start the download of the second image, and so on. So although the images would download, they'd download serially. The UI would remain responsive, it would also be completely non-blocking, but it'd be very, very slow. So what I actually need to do is resort to the task parallel library to help me out here. So I will get my collection of downloads, I will kick off all of those downloads, but I will just collect the set of tasks that represent that set of downloads into an IEnumerable here, and then I will consolidate those, or I will put a wrapper task around those using the task.whenAll method. Now that task.whenAll creates a task that becomes complete when all of the subtasks become complete. So although I've kicked off all of those downloads in parallel, I can now wait for all of them, or I can create a task that represents when all of them are completed, and I can await on that aggregated collection. So that await will only come good when all of the downloads are completed. So now when I call this, I get a task back that represents downloading that initial atom feed, reading the contents of the atom feed, downloading all of the individual images, and that task will become complete only when all of the individual downloads. Yes?
Is there a way to control the number of threads that you're going to end up using?
Not using await directly. You can, I believe that you can, if you're creating you can sort of manually create a task. So you could create a task using something like task.factory that wraps the set of tasks, the set of asynchronous things you want to do, and then you can control the number of threads on that task. But again, await will not handle that for you. And for asking that question, you get a prize. Thank you, Mindscape, for that. That's a Mindscape Mega Pack, which is a jolly good thing. Lots and lots of lovely controls. So more questions, please. Actually, I only have one more of those, so not many more questions.
I do have a question.
Okay.
So you have a cancellation, right?
Yep.
In the cancellation, why it shows a cancellation operation exception instead of some kind of messages?
Why does cancelling it throw an operation cancelled exception?
Yeah.
Because that's just the way that the task parallel library works. That's how it represents cancellation, is by throwing an exception. So because the cancellation can happen pretty much any time, there's no kind of nice exit from the API, because it's just the idiom that the TPL uses to show I have been cancelled. So yes, you have to catch that. Again, there is some control over that in the TPL. There is a throw on cancellation property in, I think, when you're starting a new task. I forget exactly where it is, but yeah, when you're kicking off, if you're manually kicking off a new task, if you write a little wrapper method to kick off an asynchronous thing, then I believe there is an option as to whether you throw on cancellation or not. Check MSDN for the details of that. I don't know them offhand. Right. Sorry, you guys. You snooze, you lose. All right. Now, the other thing that you may be interested in is actually getting a value out of this asynchronous computation. So maybe in the case of the file download, we want to know how many files were downloaded. We want to get an integer value out of that. And once again, async supports us in that. So, let's just take that. Let's get into there. And again, because this is a computation that has not completed yet, we can't just return an integer from this. We have to return a task of integer. Task of integer, or task of t, means a computation that will at some point in the future return a t, in this case, an integer. Does that mean we have to start spinning up tasks? Well, no, because all we need to do is if we return an integer from an async method, the compiler automatically translates that into a task of integer because it knows that we are not going to reach that return statement synchronously, or we will not necessarily reach that return statement synchronously. That can only be a future, that can only be a promise, and therefore it's got to be a task of integer rather than an actual integer. And so now if I kick this off, then you can see download is happening and I am able to get that number back again. I realise it appears pretty synchronous, but trust me, there was a lot of background activity going on there. So in the same way that having no return at all, or returning void, translated into a task just by altering the return type of the async method, you can return a value just by putting task of whatever as your return type and returning the actual sort of unwrapped value when it becomes available. So the flow through this will be, you start at the top, then it yields, and what it yields is a task, and eventually when that task completes, it will be resulting in that. So that becomes the result of that task. Does that make sense to people? Sorry, question there.
Yeah, if you put a thread sleep in that download image as async, it would actually be as if it's taken a long time to read the like just before the active text equals or late.
In here?
Yeah, just after the other side they're using the thread.sleep.
You want a thread.sleep in there?
They'll just simulate that it take a long time to download the image.
And I have a suspicion this is actually going to end up running on the UI thread, because that when that continuation runs, that's happening on the UI thread. But we'll give it a go and we'll see what happens. Still too fast. Oh, I need it to be on each one, don't I? There we go. So you can see, because that thread.sleep is happening on the UI thread, it's remaining unresponsive, and everything is happening synchronously, effectively. So sorry, I'm afraid it's still not going to pan out for us that way. All right. Sorry, question over there. Sorry, you're asking if the code after the await is being run as a closure? Yes. Basically it is, and I'm glad you asked me that. I wish I have got another one. I was saving that for tomorrow, but that was a really useful question. Thank you. All right. So what is happening inside the await statement? What is the magic that the compiler is doing? Well, let's imagine we've got an asynchronous method, this do something async or whatever, and we decide to call that with an await. Well, the compiler basically looks at this and goes, well, the beginning of my method, I know there's going to be no asynchrony issues there because there's no awaits in there. I'm not going to have to yield or anything like that, so I'll just compile that in the usual way. And then once I've finished the await, once the thing is returned, well, actually that's also going to be running synchronously. So I can basically build another little block out of that. And all that remains then is the glue. How does the compiler glue those blocks together? Well, I can show you a simplified version of that pretty easily. So here's an async method that kicks off an async operation, awaits on it, and then does some other work. What does the compiler turn in? So there's the C#5 code, which we just looked at. What does that get turned into? Well, first of all, it calls the method that is going to return a task, and yep, that returns a task. It then inserts this, and this is where the compiler magic starts to happen, is it then inserts this call to .getAwaiter on that task, which is a terrible name to say because it always sounds like get me a waiter. It's like call me a waiter, you're a waiter. I don't know, it's awful. But that's what it is. And that returns an object, an awaiter object. And the awaiter object is kind of that little bit of glue that does the work of the await keyword. This is kind of what the await keyword is going to translate into. The compiler then inserts a check for, has this awaiter object completed? Because if that asynchronous operation runs really, really quickly, then by the time the runtime is actually finished assigning variables back and forth, it might actually already be done. It's a really quick operation. So the first thing it does is say, have I already completed this asynchronous thing? If so, I will get the result of the asynchronous method call, get the result of the task, assign that back into whatever it's being assigned into, and proceed with the continuation. So you can see that bit and that bit are being copied pretty much verbatim into there. What if it hasn't completed by the time everything's returned, by the time we need to proceed? Well, and that's the more usual case. So in that case, it goes, right, I'll take the awaiter and I'll call its onCompleted method, and onCompleted takes a callback, it takes an action. And this is where the closure thing comes in, because what the compiler does is it constructs a closure containing the continuation. So again, you can see there's those same lines again, those same bits of those same bits of continuation, but now they are inside a lambda, or inside a callback, and that is a closure that can capture variables, and that's why things like that's how things like using statements are able to work. That's how you're able to reference variables that were declared above the await, below the await, because they are captured into this closure. They are captured into this anonymous method, this anonymous delegate, and you can continue to use them as if they were still in scope. Does that help to answer your question?
It can't be right exactly like that, because it could have still be completed between the test and the else.
It can. You're absolutely correct. And no, I really am out of Mindscape things this time. But thank you once again for leading into my next slide. The truth. It's like I've got stooges all over the place. This is awesome. It is indeed a lot more complicated than that. What actually happens is that the compiler builds a state machine, because compiler writers love building state machines apparently. I have no idea why. And it basically puts the awaiter object into that state machine and keeps and moves through it as the method progresses. And especially for you, we can actually have a look at the real truth of this thing. So let's have a look at this kickoff async operation. This dot peak, for those who've not come across it, it's like reflector, so it's a decompiler. And fortunately, it is not aware of the async keyword, so it will not decompile things into the async keyword. It will show you what is really going on, and that is what is really going on. So you can see that what I showed you was indeed quite a simplification. If we want to look at that state machine itself, well, that's pretty unnerving, but we can have a go. The magic is basically happening in here, inside this move next, this async state machine move next method. You can see we've got a task awaiter in there. You can see it begins by calling that async method. It calls getAwaiter on the task that comes back from that. It checks the is completed, and if it's not completed, then it kicks off this method builder await on completed with the state machine and the awaiter. And that's basically going to fall through to where the actual continuation happens, which is all the way down here. You are not expected to understand this. Hurrah! Because this is all taken care of inside await by the compiler. You're absolutely right. There is the potential for, in what I showed you, there is potential for a race condition between is completed and the callback. But in practice, the generated code is such as to take care of that possibility. Even if that condition arises, it will still come through with a continuation. Just it will happen asynchronously, which you're already expecting. So what about this getAwaiter method? Well, the task parallel library's got this built in. So in .NET 4.5, they've added a getAwaiter method to task. It doesn't actually need to be an instance method. So as with link, if you're familiar with the transforms compilers do for link, all it's doing is it's basically saying, I'm going to take that expression, I'm going to put .getAwaiter on the end, which means that it's perfectly okay to have an extension method. So if you use like async bridge to make this stuff work on 4.0, the 4.0 task class does not have a getAwaiter method, but things like the async bridge and the async targeting pack add an extension method to task, a getAwaiter extension method to task, so that it can support the transformation that is required. And I can actually show you that it's not too hard to implement your own custom await. So if you've got some kind of asynchronous activity that's not covered by the task parallel library, then you can still use that friendly await syntax as long as you just implement an awaiter of your own. So here's a custom awaiter for process. So rather than a task running in your own process, you can actually kick off an external process and await on that while remaining responsive. So it's pretty simple. I'm adding an extension method to the process class, which just returns my new custom process awaiter type. I just need to implement three things on it. I need to implement this is completed, Well, that's pretty easy. I just check, does that shell process, does that external process, has it exited? I need to implement getResult, and in my case, I'm saying that the result is just going to be the exit code of the process. You could capture something from standard out or whatever, but I'm just going to use the exit code. And I need to implement this onCompleted, which takes a continuation. That continuation represents the rest of the stuff that happens after the awaits. This is the closure that we were talking about earlier. And in my case, I'm going to be pretty naive about it. I'm just going to hook the process.exited event and run the continuation on the exited event. So now I can jump in here. And now, by using that extension method, I can write code that looks like this. I'm going to start a process, I'm going to do some stuff, I'm going to await on that process, and then I'm going to do some more stuff when that process exits. So I can kick that off, click go, it runs Notepad. You can see that the before code has run. You can see that although I'm still inside this method, I'm still inside that await, my UI is still responsive, and then when I exit Notepad, it captures the exit code, and the rest of my asynchronous method runs. Now you may say, well, that's all, that's no big deal. We can do that with the process.exited event anyway, and you're absolutely right. All I'm doing is putting a thin layer over the exited event and the has exited property to avoid that need for callbacks. I've put my business logic in a top to bottom way. I put my flow logic in a way that you can easily read without having to worry about events or separate things happening or different blocks of code. So this gives you a unified way to use any kind of asynchronous thing. It doesn't have to be a task, it doesn't have to be an async operation. You can do it for anything if you want to, if you need to implement a custom awaiter. Async and await, so we've already talked about some of the stuff that async and await don't do. I wanted to mention a couple of other things. Firstly, they don't really provide a way to do parallel processing. You can kind of do that by kicking off a bunch of async things and then doing an await on all of them by doing that task.whenOr. But basically, you're going to have to get the TPL involved. You're going to get the task parallel library involved, or use something like parallel link. And there's no shame in that. It's not the wrong solution. It may look like you may feel like you want to use the language keywords all the time because they're so much more convenient, but realistically the library is the right place to be solving a lot of these things. That's where you've got the control over parallelism, the control over concurrency. The other thing that async and await won't help with is if you've got collaborating asynchronous activities, collaborating asynchronous operations, which need to coordinate by, say, sending messages to each other. If you've got, say, a couple of different threads doing stuff, and one of them has got to wait for the other one to finish something and hand over a result, which it can then use to continue with its activities, that's going to be really hard to do with async and await. It's not built in with async and await. You're going to have to build you're going to have to build your own out-of-band communication system for those two to signal to each other. And we'll talk about that a little bit more in a moment. So we've covered the language constructs for async and await, and I just wanted to kind of highlight the stuff that the options you've got for shifting computations in time beyond that raw sort of task or async operation behavior. So what we've been talking about today has basically been what a lot of people call futures and what .NET calls tasks. That is computations in progress or computations whose results will become available at some time. They're just going on in the background somewhere, and at some point a result will become available on that future object. But there are a bunch of other things that you can do to move computation away from from blocking your main thread, from blocking your UI thread. One example in the .NET framework is delays, which is .NET knows as lazy of T. Now these are they're not actually asynchronous in that when you evaluate a delay or a lazy, that evaluation happens on the thread where it's needed. But this is a way of deferring expensive computations that might not be needed. So if you've got something which is going to be slow, it's going to be computationally intensive, and you don't know whether you're going to need it or not, you can delay that using a lazy. You can shift it far enough in the future that maybe it won't ever be needed at all, and you'll be saved the effort. Another concept which I don't think has got an implementation in .NET, that'd be easy to write one, is the idea of a promise. A promise is a little bit like a future, a little bit like a task, except that if you try to evaluate it, then it will block. So it's something where a typical example is a value that's going to be filled in by another thread. So there might be a task running in one thread that's going to post something into a promise on another thread. And it's okay for that first thread to block in the name of synchrony. Now, with the advent of async and await, there's usually much less need for blocking. But if you've got something like that, then a promise can be relevant. Another example, which is pretty powerful, is agents, and these are kind of concurrent objects. So when you've got an agent or an actor, it internally thinks it's running serially. It internally thinks it's running kind of in its own universe, doing its own thing, and that gives it a great sense of isolation. It means all of your side effects are insulated from affecting sort of global state, so you don't have contention between different agents. Each agent is private to itself, but they're running on different threads. They can post messages to each other, and therefore you can get that coordination that I said was not really built into async and await. Now, agents and actors are not built into the .NET framework, but there is an implementation available. Just you need to jump into F# to get it. And those of you who know me knew that this was coming. So I won't go on about this for too long. So F# introduces the mailbox processor type. And don't get too hung up on the language differences. A mailbox processor, it's basically a class which has a function that just runs over and over again. So here, for example, is a logger, which it just sits, once it's kicked off, it just sits in this loop. This is, the funny syntax there is basically F# equivalent of the async and await keywords. The let bang is basically an async, it's basically an await. So I'm saying I want to wait until I've got a message coming into me, and I'm not going to block my thread while I'm doing it because I'm using this let bang, using an await. And when I get one, I'm going to decide what to do with it, and then I'm going to call my loop function again. So this, when it gets started, will just run this function endlessly on its own private thread. It's got its own private state, in this case the count variable, and it can coordinate with other agents by sending them messages. So for example here, it can post a message to the email agent because we've had an error and we want the email agent to pick that up. And that again is non-blocking, that asynchronously posts the message to the other agent, the other actor, and the logger can keep going while the email agent ticks away in the background. Again, completely isolated from each other, completely independent of each other, completely safe from interfering with each other, communicating only by these asynchronous messages. There's also some options around for asynchronous processing of data. If you may be familiar with the reactive extensions, they've been described as linked to events. And they provide the reactive extensions provide a very, very rich set of operators for processing sequences on a subscription-based push model rather than the pull model. And again, this ties in with this whole non-blocking theme. If, say, you're receiving messages off a queue, then the only way to do that with link is to block while you're, so you'll do it, basically you'll have an enumerable representing things. Whenever link wants to get the next thing off the queue, that enumerable will block until there's a message available. So if you've got unpredictable messages coming in, you don't want that pull model. Instead, you want to get something pushed to you every time a message arrives, and that way you're non-blocking. The reactive extensions do exactly that. They are very much like the link operators, but they work much better with those asynchronous, unpredictable inputs. Another thing to be aware of, which came in with .NET 4.5, is TPL data flow. This is a set of building blocks where you can basically you can string them together. So you can say, I've got some input blocks which I can feed data into. I can join up my input blocks to processing blocks, transformation blocks, and output blocks in a graph. I can split data so that it goes down multiple routes at the same time. And it's a great way to process, again, unpredictable data or bulk data, again, without blocking your main thread. So, where do we stand? Well, we've had the asynchronous versus synchronous thing since .NET 1.0, and indeed long before then, I guess. In our hearts, we all know that making blocking calls on the UI thread is a naughty, naughty thing to do. But we all do it. We all do it because it's so much easier. Because writing the async code is just a pain. That's no longer an option. Even if you think, oh, it doesn't affect me because I'm always dealing with small files, I'm always dealing with local resources, it's going to be fast enough. The technical option is being taken away from you. The APIs are going away. If you're using Silverlight, yeah, right, that's going to happen. If you're using Silverlight, if you're using Metro, if you're using Windows 8, the Windows runtime, you are no longer being offered synchronous APIs. You do not have the option to cheat anymore. You have to use asynchronous APIs. So the language support is really important for that. Unfortunately, that new language support, the async and await keywords, make it pretty much as easy to write asynchronous programs as to write synchronous ones. We don't need to cheat anymore because with those keywords, it's just as easy to do the right thing as to do the wrong thing. So you can create that great user experience, that fluid user experience, without having to complicate your code, without having to make your code difficult to reason about, without making your code difficult to understand. It's seamless, it's self-describing, it runs top to bottom, it's very simple, it's very easy to prove what's working. So I think it's going to be a huge thing for people who, we're all working in distributed space now. I think it's going to make our lives so much easier and our user experiences so much better. So thank you very much for your time. You can get hold of me on those addresses, and just to let you know, by the way, that Green Button is hiring. If you're interested in working for a cloud startup, then ping me and I'll put you in touch with relevant people. Thank you very much for your time.